Well, good morning and happy Friday. So, we've talked about a number of processes. We've talked about rapid mix, we've talked about coagulation, flocculation, sedimentation, disinfection, and filtration. These processes are also applicable in wastewater treatment. And the theory is identical, whether you're looking at a water treatment plant or a wastewater treatment plant. So what I'd like to do is talk about the goals of wastewater treatment. We'll look at each of the individual processes. We'll look at how each of these processes operate, some of the challenges in wastewater treatment. Some of these challenges are very different than in water treatment. And we'll look at some of the types of secondary treatment that are used in municipal wastewater treatment. So when we're talking about municipal wastewater treatment, for the most part, what we are talking about is domestic wastewater. So for instance, for a plant like the City of East Lansing's plant, that is predominantly domestic wastewater. There are a few industries, but not very many. Now, when we're looking at treating this wastewater, fresh sewage is typically kind of a gray in color. So to have an odor of freshly turned earth. The problem is that's not what we're often dealing with in a wastewater treatment plant. For instance, the East Lansing plant treats water from East Lansing, but also Meridian Township. It treats water from all the way up Grand River, east on Grand River, beyond, I don't know if you know Grand River, beyond Cornell Road, beyond there's a St. Martha's Church. So it's a significant distance from that point to the East Lansing treatment plant. Not surprising, that results in the presence or the absence of oxygen and sewage going septic. So for the East Lansing plant, one of the challenges that they have to deal with is this very long residence time in the sewer system. And that results in sewage that's black in color, has a rotten egg odor, and that's because of the presence of hydrogen sulfide and mercaptans. So what's happening is the wastewater goes anaerobic, a lack of oxygen, and then you start getting anaerobic organisms proliferating, and the reduction of sulfate to hydrogen sulfide and sulfur-containing amino acids to mercaptans. Temperature of domestic wastewater typically is fairly constant, typically at about 10 to 20 degrees C. And what we are often looking at is a biochemical oxygen demand. And we're looking at reducing that. For the most part, that's the goal. In the scavenger hunt, you were asked to look for the outfall of the East Lansing wastewater treatment plant. You saw that it flows into the Red Cedar. The point that the Red Cedar, where it flows into the Red Cedar is not a very large body of water. So we need to make sure that the biochemical oxygen demand, or the amount of organics present in the water, that when the microorganisms degrade that, consume oxygen, is not to the point where it will have a detrimental impact on the body of water. This is a table from your textbook. I put it in here just to give you a sense of the composition. And let's just look at a few parameters, for instance, BOD. So typical BOD of most untreated domestic water, so this is the water that enters the plant. For most plants in the US, we're talking about 200 milligrams per liter. And notice it's milligrams per liter of oxygen because we're looking at the usage of oxygen. In systems that have significant amount of water conservation measures, you'll typically see much higher levels, and in weak, you'll see lower. If we look at suspended solids, it's fairly similar, about 210. And I've highlighted these because in terms of treatment, this is often what the two parameters that we use for treatment. The other parameters that we want to think about are phosphorus and nitrogen. Why do we care about phosphorus and nitrogen in particular? We said here with BOD, we're looking at the consumption of oxygen by the microorganisms in degrading organic matter. Why do we worry about nitrogen and phosphorus? What is it about nitrogen and phosphorus that is of significant concern? Okay, so eutrophication. What is eutrophication? I want to make sure that I can hear you. Okay, so eutrophication is caused by the excess phosphorus and nitrogen in water. It is a process where a body of water changes over time due to eutrophication or due to excess primary growth from a lake eventually into essentially a swamp, and eventually can become dry land. So it's a complete change in the ecosystem. We worry about it in terms of drinking water treatment because of the algae blooms. We talk about hazardous algae blooms. So we talk about this in terms of a body of water, excess phosphorus and nitrogen resulting in increased primary productivity, increase in the release of exotoxins by the algae, and that makes the water unsafe to drink. So for instance, a few years ago, Toledo had to shut down its drinking water system for about 3 days for the entire city of Toledo because of hazardous algae blooms in Lake Erie, resulting in unsafe drinking water that they couldn't treat and protect public health. We want to make sure we're avoiding those situations. I included this here just to give you a sense of the differences in the characteristics of the BOD with treatment. This C stands for carbonaceous. It's one of those. Must be Friday. The C stands for carbonaceous and the N for nitrogenous. So what we're looking at here is we're degrading the organic matter that contains carbon. So we're looking at degrading carbon to CO2. Here we're looking at degrading that organic material from ammonia to nitrite to nitrate. So what you see here is an untreated sewage. You really don't start degrading that nitrogenous material until about day 7. So up until about day 7, anything that you're degrading is predominantly the carbonaceous material, the material that contains carbon. Think of it as glucose. And that's degrading. to ultimately, in the presence of oxygen, to produce CO2. After about 7 days, you start degrading the amino acids and the proteins. So you start degrading the nitrogenous material. The treated sewage, notice after about maybe a day and a half, you start degrading that nitrogenous material. And that's because most of what we focused on in the treatment is that carbonaceous material. So in oxidizing that carbonaceous material so that it doesn't exert an oxygen demand, it isn't consuming oxygen in the receiving body of water. Now we also can look at industrial wastewater. And this is again from the textbook. Also added some information about brewing beer. There's lots of microbreweries in the opening up in Michigan. And one of the challenges with industrial waste is, notice we said that the raw municipal wastewater has a BOD of about 200 and about 210. This is municipal. Notice for much of this industrial waste, the ranges are great, but the levels can be much, much higher. So for instance, one of the challenges, we'll look at microbreweries, one of the challenges there is that, number one, beer brewing is a batch process. So they're not releasing the waste from the brewing process all the time. They're producing beer. When it's produced, then they have the waste that they discharge. So it's a high load over a short period of time. And that can have a very significant impact on wastewater treatment. So for instance, in Williamston, they've had to deal with Old Nation and work very closely with them because as Old Nation has increased its production, that brewery wastewater has a very significant impact on the operation of their treatment plant. And when they first opened, when you visit the plant, you could actually kind of smell the brewery wastewater at the treatment plant. So it kind of smelled like beer, stale beer at the treatment plant. So we need to think about what impact this will have on the treatment plant itself. So as a result of that, EPA has developed extensive set of pretreatment requirements for industrial wastewater. These are developed federally, implemented on a state level. So in Michigan, EGLE is the agency that has primacy. It has the responsibility for enforcing these regulations, and they work very closely with the utility. They work often closely with the source, the industry, to try and develop the best approaches. So the whole goal is to prevent the introduction of pollutants into the sewer system where those pollutants would interfere with either the operation of the plant or the disposal of municipal sludge. So for example, a landfill is essentially an industry. Mentioned that Mike Ellis will talk about PFAS. One of the challenges is the presence of PFAS in effluent from a landfill. If that effluent is discharged to the municipal treatment plant, that PFAS can end up in the biosolids, and that has a significant impact on what can be done with that biosolids, how they can dispose of it, whether they can land apply it, can't land apply it, because we worry about the accumulation of those PFAS chemicals in the plants that are grown on the land where the biosolids are applied. So we have these really strict rules. And what we're looking at, one is, as I mentioned, issues in terms of accumulation in the biosolids. We're also worried about the health and safety of both the population near the sewer, and every one of us, if we're in an area served by sewers, have sewers out in front of the house. But they're worried about that, and they're worried about the health and safety of the plant operators. So, for instance, there are requirements regarding the flash point. You don't want to release pollutants that can react, can explode, especially if you're producing hydrogen sulfide. There is a significant potential for an explosion. You don't want waste streams with a pH of less than 5, and this is because of corrosion. Corrosion of the sewer system, of your sewers, results in leakage that potentially results in contamination of your groundwater supply, soils around the sewer system. You also don't want to put in solids or viscous pollutants that would obstruct flow. And that's true for municipal systems or industrial systems. Thinking about the municipal system, anyone want to guess what is, from a home use, what is essentially a bane of existence for wastewater operators? What causes significant problems for those operators? That you can discharge from your home. Exactly, people flushing wipes. Flushable wipes are not flushable. Despite what it says on the packaging that they come in, and I'll show you a picture in a little bit about what flushable wipes do to the treatment system. But they clog pipes, and they get caught in the pumps, in the pipes. So one of the things you don't want to do is you don't want to be flushing wipes. Another thing that causes problems are oils and grease. Another thing you should not be putting down the sink are oils and greases. So Saturday morning, you get up, you decide it's a great morning to make some bacon and eggs. What do you do with the bacon fat? It's a little life lesson. Exactly. Drain it into a cup. I keep like old empty spaghetti jars, sauce jars, and drain it in there. When it fills up, seal it up and put it in the trash. Okay. Oils and grease cause major problems. The oils actually congeal in the sewer system, and you can end up with massive grease balls in the inside of a sewer, and these can be hundreds of feet long. They clog the system, and then the oils are difficult to remove. So another thing not to put down the sewer are any cooking fats. And then you don't want, in terms of the industry, you don't want to be, we don't want them releasing chemicals that would produce toxic gases, vapors, and fumes. And then another thing that's regulated is the discharge of any trucked or hauled pollutants. This is similar to the issue that I mentioned with brewery waste. That's a batch process. That means that there is a slug of pollutants entering the treatment plant. And for the most part, we're using microorganisms. That slug of pollutants can be toxic to the microorganisms, which means you upset the treatment plant and it's not working properly. The way we regulate in the US is based on a total mass discharge limit. So a treatment plant has a limit of what it can discharge, typically in milligrams per liter, but also in mass per day. And that's because what we do in the US, and this was developed about probably 25 years ago, as an attempt to look at a much more systematic level of treatment in a water source. So they look at monitoring water quality, ecosystem health, fish tissue. Based on that, they then evaluate that data and look at both point sources, so that outfall from that waste from the East Lansing wastewater treatment plant, for example, and non-point source. So what do we mean by non-point sources? What's an example of a non-point source? Actually, you saw the agricultural land. So, for instance, on the scavenger hunt, you looked at the buffer zones along the Red Cedar. What's the purpose of those buffer zones? Why were they put there? So intercept rainwater, but also to intercept stormwater. So you're looking at intercepting and using the plants to, for instance, consume some of that nitrogen, some of that phosphorus from your stormwater runoff, thereby reducing the load to the water itself. So if we can have here, we have this, here's our river, and then here's our buffer zone. And whether it's agricultural land or residential land where people are fertilizing, we have this buffer zone here. So what we can do is reduce the amount of nitrogen entering the river because the plants in that buffer zone consume nitrogen and phosphorus. So if we can reduce that load, then we can improve the water quality. And this is BMPs, or best management practices. One of those could be the use of buffer zones. That reduces our non-point source. We're regulating our point source at the treatment plant, and we can improve the quality of the river water. Apparently, and I wish I could find photos of it, but apparently in the 1960s, before the Clean Water Act was implemented, before EPA was formed, it was not unusual for students walking along the Red Cedar to see toilet paper, human feces floating in the river. Why? Because there was no mandatory requirement for treatment. And if you couldn't meet the demand for the treatment plant, you could just discharge straight into the river. Again, this is from the textbook. This is the equation, but basically the thing is you're looking at your point sources, you're looking at your non-point sources, and then we have a margin of safety, and that's how we determine the total mass or total maximum daily load. So let's just kind of think for a minute. If we're looking at the treatment system, mention some of these. What are the contaminants that we are going to target for removal? Sure. So the main thing to know about this is that you're looking at your point sources, you're looking at your non-point sources, and then we have a margin of safety. This is a very, very complicated process. We're not going to go into it in any depth beyond this, but I want you to know that in determining these total maximum daily loads, we're looking both at point and non-point source. Initially, we only looked at point sources, and over time, we realized that we couldn't control pollution. We couldn't maintain the quality of our bodies of water unless we looked at non-point sources too. So what target, when we're looking at, and we'll focus on municipal wastewater treatment. What are we looking at to remove? What's the goal? I'll let you think about this. Okay, I've mentioned a number of issues. So we have our sewage coming in. So this is municipal sewage. We have some sort of treatment process. You saw the outfall, and here's our receiving body of water. What are we looking at removing? So from an engineering perspective, what do we want to remove in the system? Okay, 1, suspended solids, phosphorus, nitrogen. What else? So we want to remove suspended solids. Why? What's the concern for suspended solids? Why not just allow that material to be released? 1, it can contain organics. And if it contains organics, it can consume oxygen in the process of being degraded. It's also harmful for wildlife. It will settle on the bottom of the water bowl. And that changes what we call the benthic zone, so for instance, if you have a rocky benthic zone, that bottom of the river, now you fill in the rocks, and that changes the habitat. So for certain organisms, fish, for instance, they need that rocky zone in order for the fish to hide from predators. That no longer exists. So it significantly changes the habitat. Another reason is you can have either organics, you can have metals that are sorbed to the suspended solids. And if you don't release those, then you're potentially releasing those organics and metals to the receiving body of water. And over time, those metals can dissolve, they can be released, they can be bioaccumulated. So if they settle, and then you've got benthic organisms, and those metals can potentially bioaccumulate. Same with organics. For that reason, we don't want to release suspended solids. How about nitrogen and phosphorus? And I've mentioned this before. So why don't we want to release nitrogen and phosphorus? Exactly, eutrophication. The other contaminant that we didn't mention contains organics but just organic material. And we typically refer to that as biochemical oxygen demand. Because we're looking at, so for instance, if we look at glucose that reacts with oxygen, so it's consumes oxygen in the degradation to form CO2 plus H2O. 6 moles of CO2 produced for every 1 mole. What I've shown is glucose. We have 6 moles of hydrogen, balanced hydrogen. We've balanced carbon. And let's see, we have 12 plus 6 oxygens there. So we need 6 moles of oxygen for every 1 mole of glucose we have in the water, just to give you a sense of how much oxygen we need. So it's a significant amount of oxygen that's required by these microorganisms. So we want to reduce the amount of organics so that we reduce the oxygen demand. We don't want the body of water to go septic, which means that it doesn't have oxygen. There are other contaminants. We mentioned oils and grease. So we also want to remove, and actually you'll see it abbreviated as FOG, fats, oils, and grease. Okay. We don't want that being released to the body of water. So what we will do kind of as we today and then also through next week is we'll look at wastewater treatment. So we'll look at a number of facilities. I'm going to try and move back and forth between some of these processes and some videos to better show you the process, since we won't be able to tour a facility. So let's just start by looking at the treatment process itself. We talk about pre-treatment, primary treatment, secondary treatment, and tertiary treatment. Think of primary treatment as the removal of material that is going to harm the processes downstream. So we want to remove large material, rags, those non-flushable wipes that people flush down the toilet. Toilet paper. It's really interesting. It was kind of interesting to me. When I was on sabbatical in Taiwan, I was actually really surprised that they don't flush toilet paper down the toilet. They have a little garbage can next to the toilet, and that is where they dispose of the toilet paper, and they just dispose of that on a daily basis into the trash. It's just interesting that I grew up, you always flush the toilet paper down the toilet. There are other ways of actually processing it. Mentioned the fats, oils, and grease. Anything that gets to the sewer, we want to remove in this process. And then we also may equalize the flow and the strength of the waste. So nighttime, when the question is asked, does the toilet paper go to the landfill? Then yes, exactly. It goes to the landfill, or incineration if incineration is used. In Taiwan, because of it being densely populated, they use incineration much more than we do. But that toilet paper doesn't exert an oxygen demand on their treatment system. So we want to equalize the strength. People use less water at night, or maybe during the middle of the day in a normal situation. I think flows are more consistent now, simply because people are home more. But you want to equalize both the flow which changes during the day, and also the strength. So at night, when people are sleeping and they're using less water, the water will have a higher strength, it's higher BOD, and a lower flow. So thank you, Calissa. Calissa just mentioned that in Costa Rica, there too, they don't dispose of toilet paper in the toilet itself. They dispose of it as trash. So it's just, like I said, it's sometimes we kind of think that everything's done the same way everywhere, but it's not. So let's look at these processes. What I'm going to
stop brings us to our headworks facility. This is where all of the wastewater from out the city comes to our facility. Here, we remove large items such as rags or paper towels and grit, which can pose issues to the treatment system further on. Let's go inside and take a look. This is the bar screen. The bar screening system picks up paper towels, rags, and puts them onto a conveyor belt to be hauled to a landfill. The grit and rags that are collected from the bar screens enters the grit box, which will be hauled off to a landfill for final disposal.
Cans, bottles, small sticks, and rags. We send up to 4 truckloads of this debris to landfills every week.
So I just wanted to play that fairly quickly, and I don't know why there's this bar in the middle of the screen. I apologize, but I wanted to give you a sense of these bar screens and how they work. So here's a photo of the bar screen. So the purpose of this is to remove larger objects. That solid material is then sent to a hopper. So these are mechanically or manually cleaned. And these are screens that have openings of about 1.5 to 2 inches. They're catching that large material. That may be twigs, other material from a combined sewer system that flowed into the sewer. They can be things like the toy that the little kid flushed down the toilet. We also have comminutors, and these are devices that essentially try and grind up the material so that it doesn't clog the pumps or the piping network downstream. And you can see here we've got a comminutor right here, essentially in the pipe. This is the grinder from the East Lansing wastewater treatment plant. I took the picture one of the tours of the plant. And there's a number of things to observe in this. Is one, these are those flushable wipes that clog the grinder, they get stuck in it, and then somebody has to pull this out of the piping network and clean that device. And you can imagine that's a pretty awful job. The other thing that happens is you get erosion of these plates, and obviously they're not as thick, they're not going to work as well. And you can see that they're not even evenly eroded depending on the flow. So I will stop there, and happy to stay on and answer any questions. And what we'll do, like as I mentioned, for the next few days is what we'll do is we'll essentially move through the wastewater treatment plant, looking at the various different devices that we use to treat wastewater.